Okay, let's look at another approach for performing imitation learning or robust imitation learning without assuming access to an interactive demonstrator, so only offline set of demonstrator. This will follow the MaxEnt principle that we previously discussed. And we'll try to maximize the entropy over the trajectories that might be sampled from our given policy, the policy that we are training. So we know that a policy induces a distribution over trajectories, right? What we used capital P of tau given a policy previously, and this is a valid distribution. That is all trajectories, the probability for all trajectories do sum to 1. Our goal here, in this case, would be to come up with a policy. Okay, so this is not an inverse reinforcement learning approach. We're not trying to learn a reward function, but we're trying to compute, to find a policy that results in the same distribution of trajectories as our demonstrator policy. Okay, so this can be defined here. The expected mu over pi d equals the expected mu. This is a sample-based expectation by following our current policy and computing the expected trajectory over samples, right? And we're going to use the maximum entropy principle, where the probability distribution, meaning that we're trying to discover, to return the probability distribution which best represents the current state of knowledge and is the one with the largest entropy. Actually, it's the principle states that the one that represents the knowledge the best is the one with the largest entropy, and indeed we'll try to converge on a policy that results in the same distribution while retaining the maximum entropy during training, right? While we train. So let's see how we can use the MaxEnt approach for imitation learning. So this is a paper by Zybert et al. From AAAI 08. We would like to find a policy which results in the trajectory distribution, the same trajectory distribution, similar to the expected one by the demonstrator policy, without overcommitting, while remaining maximum entropy, right? So indeed, this is the optimization problem that we are solving. We'll try to maximize the entropy of our policy. Hope you remember that this is the definition of the entropy of a distribution, right? Subject to, well, under what constraint? We would like the distributions to be the same. The trajectory distribution that we sample, right? And this is the trajectory distribution that is defined by our policy, the policy that we are training, and the trajectory distribution from the demonstrator. Actually, specifically here, we're setting the expected value to be the same. So the expected trajectory under the demonstrator is the same as the expected trajectory under our policy, right? And this is our constraint. So we'd like to maximize entropy while having the expected value, the expected trajectory similar. So in the original paper, they considered a linear approximation for the policy that we are training. We know that the linear approximation is somewhat limited. I mean, it's one thing to assume a linear approximator for the reward function. It's a different one. I would say it might be a more constraining assumptions to assume a linear approximator for your policy, the policy that you're trying to train. But the same approach, the MaxEnt approach, can be generalized also to work with deep networks, policies, and the full details can be found in, for instance, in this ICML paper from 2016.